as mentioned before, it's a friction drive, meaning that the way it's held in place is dependent upon the friction between the back plate and the screw of your chuck and then the ends of your core. So there's a screw at the very back there, and that just kind of rests up against the chuck. I believe it's a 1/4 screw with a half-inch shank probably. The shank runs in the bushings of this sort of housing here. There's 2 bushings located side by side, separated by a small washer. In here, and here is your bushing retainer, or not your bushing, your bearing retainer. You can see the bearings there. I'm going to rotate that sort of bit. The screw head there rotates, so the screw head acts as the shaft. This is pretty solid, very smooth sort of motion. These screws here are screwed into a captive nut contained into this plate here. This plate at the back has cutouts for a 440 nut, and you just press those guys in and they're good to go, and you can screw and unscrew these as much as you want without the need of a wrench. So it's easy to assemble in that sense, or interchangeable. In terms of, actually, let's get onto this side first. So on this side, you have a back plate there. That's just the other end of your friction device. The separation between the back of this back plate and this plate is 5 millimeters as specified. I believe it's like 5.02 or something like that. Like, it's very close. Maybe a couple thou out of tolerance, but not bad for a 3D printed and laser cut part. So this whole assembly here, again, you can see some captive nuts that holds the 440 screws in place. Is mounted onto this flex coupler by 2 screws that's threaded into where the set screws used to be in it. So then the flex coupler mounts onto your stepper motor, and your stepper motor does the rotation of the core. Back here, if you want to remove that flex coupler and whatnot, you can always do so in this slot here that provides access to the The dimensions of this device are entirely adjustable. If you say want to adjust the length of that boss from say 5 millimeters to 10 millimeters, you can put a 5 millimeter shim right here, and you'll get that adjustment. Same goes here. If you want to, 5 mil to 10 mil, then you can get that adjustment there as well. So it's very adjustable. If you want to adjust the radius of your core, you can do so by easily swapping out these plates to maybe a slightly larger diameter, and it'll accommodate it all. Or if you just want to change the length of your spool, then you can always adjust kind of the placement of this whole housing here as you would like to. So on this end of the screw, there's a stopper nut here that fixes the length of your screws, so when you screw it in, it stays the length of the jam nut to make sure that when you screw it, it's not going to unscrew itself. You know if it did that. So the motor is mounted with some M3s. They're slightly long, so we used some standoffs, just some Delrin standoffs that came with an electrical hardware kit to offset that distance. In terms of the housing itself, it is supported using some bushings, just some brass bushings on some 8 mil linear guides. They're just steel case hardened, and they were pulled from a 3D printer, scavenged from a 3D printer, but they're fairly cheap online. In terms of, I think that's everything covered for the core rotation. As mentioned, it's driven by a stepper motor, if I haven't mentioned it yet, but that should be everything for that. In terms of the carriage itself, what does all the tensioning and guiding and stuff like that, and traversing of the wire, it is driven by the rotation of the lead screw. The rotation of the lead screw is controlled by a stepper motor, and if you rotate the stepper motor at a constant velocity, then it's going to traverse at constant velocity. So that can be tuned to make sure that for whatever wire diameter you have, you can always change those parameters, and you get a desirable linear velocity here of the carriage. There's 2 linear guides, again, ground case hardened, to make sure that this doesn't sort of torque away when you go to rotate your lead screw, and ensure smooth guiding and alignment. There's some linear bearings down here to make sure that the motion is quite smooth, and you can see your lead screw nut is held captive in this sort of bottom housing here. And then on either end of the lead screw, there's some brass bushings, and those are just there to keep it located radially and make sure that there's no slop and that it runs nice and smooth in this housing. And it also ensures that over time you're not going to get wear, because if it was just plywood, over time it'd wear away.
design, we powered the device with an AC to DC power supply, so the user doesn't have to worry about batteries. And the electrical components consist of 2 stepper motors, 2 limit switches, rotary encoder, and the Arduino board, which controls the winding process. Each of the stepper motors have a driver shield, which regulates the amount of current supplied to the motor. The 2 limit switches are mounted on the ends of the core base travel distance, so the base and the edge of the carriage. When they are triggered, the Arduino will receive a signal and it will reverse the direction of the lead screw motor so that another layer can be produced. The rotary encoder is used to set the wire diameter and the number of layers by the user. They can turn it, and the Arduino serial monitor will display the wire diameter, and then once they have chosen the appropriate one, they can click it and then rotate again to select the number of layers they require.